previously unseen data, making possible applications that range from recognizing pictures of cats and dogs to creating, potentially, autonomous cars and other technology. Machines can learn because of the extraordinary confluence of math and computer science, with more than a dash of physics and neuroscience added to the mix. Machine learning, ML, is a vast field populated by algorithms that leverage relatively simple math that goes back centuries, math one learns in high school or early in college. There's, of course, elementary algebra. Another extremely important cornerstone of machine learning is calculus, co-invented by no less a polymath than Isaac Newton. The field also relies heavily on the work of Thomas Bayes, the 18th century English statistician and minister who gave us the eponymous Bayes' theorem, a key contribution to the field of probability and statistics. The work of German mathematician Carl Friedrich Gauss on the Gaussian distribution and the bell-shaped curve also permeates machine learning. Then there's linear algebra, which forms the backbone of machine learning. The earliest exposition of this branch of mathematics appears in a 2,000-year-old Chinese text, 9 chapters on the mathematical art. The modern version of linear algebra has its roots in the work of many mathematicians, but mainly Gauss, Gottfried Wilhelm Leibniz, Wilhelm Jordan, Gabriel Kramer, Hermann Gunther Grassmann, James Joseph Sylvester, and Arthur Cayley. By the mid-1850s, some of the basic math that would prove necessary to building learning machines was in place, even as other mathematicians continued developing more relevant mathematics and birthed and advanced the field of computer science. Yet few could have dreamed that such early mathematical work would be the basis for the astounding developments in AI over the past half-century, particularly over the last decade, some of which may legitimately allow us to envision a semblance of the kind of future Rosenblatt was over-optimistically foreshadowing in the 1950s. This book tells the story of this journey from Rosenblatt's perceptron to modern-day deep neural networks, elaborate networks of computational units called artificial neurons, through the lens of key mathematical ideas underpinning the field of machine learning. It eases gently into the math and then, ever so slowly, ratchets up the difficulty. As we go from the relatively simple ideas of the 1950s to the somewhat more involved math and algorithms that power today's machine learning systems. Hence, we will unabashedly embrace equations and concepts from at least 4 major fields of mathematics: linear algebra, calculus, probability and statistics, and optimization theory, to acquire the minimum theoretical and conceptual knowledge necessary to appreciate the awesome power we are bestowing on machines. It is only when we understand the inevitability of learning machines that we will be prepared to tackle a future in which AI is ubiquitous, for good and for bad. Getting under the mathematical skin of machine learning is crucial to our understanding of not just the power of the technology, but also its limitations. Machine learning systems are already making life-altering decisions for us, approving credit card applications and mortgage loans, determining whether a tumor is cancerous, predicting the prognosis for someone in cognitive decline, will they go on to get Alzheimer's, and deciding whether to grant someone bail. Machine learning has permeated science, too. It is influencing chemistry, biology, physics, and everything in between. It's being used in the study of genomes, extrasolar planets, the intricacies of quantum systems, and much more. And, as of this writing, the world of AI is abuzz with the advent of large language models such as ChatGPT.